Okay, so that was the first test. We looked at the temperature rise over the last 100 years or so when we've got good temperature records. And it seems to match what you'd expect. It gives us a climate sensitivity, but it's only one temperature rise. Maybe something else is going on here. It might be better if we could actually look further back in history and see more changes in temperature and see if this is just a one-off fluke at the moment. Are temperatures changing for other reasons, or is CO2 a regular thing that changes temperatures? But how can you actually work out what the temperature was 500 years, 1,000 years, 1,000,000 years in the past? And curiously, it turns out you can, and this is such a cool story. This is called the study of paleoclimates, climates in the past. Now, the first way this was worked out was using tree rings. If you slice many trees, and not, it turns out, most Australian eucalypts, they grow in rings each year, and you can look at the thickness of each ring, and that tells you how well the tree grew that year. If it was a good year with lots of rain and nice warm temperatures, it will grow a lot, and you have a thick ring. If it was a bad year, there'll be a thin ring, and you can count the rings. And this has been done around the world. You can calibrate this. You can look at the growth of trees recently and see exactly if it grows by 4 millimeters, that must mean the temperature was in this range or the rainfall was in that range or some combination. So you can calibrate it. Trees in certain regions are more responsive to temperature, like near the snow line, so it gives you almost a pure temperature measurement. It's a temperature that means they grow or do not grow. They've got plenty of water. In other regions, like deserts, it's the water that makes a difference, and the temperature doesn't matter. So you can actually separate out the rainfall and the temperature changes, and that's definitely been done. This doesn't really go far enough back to be very useful for measuring climate sensitivity, but there are ways to go much further back. One is to take ocean floor cores. Here is a drill that's used, it's put into the bottom of the ocean, and in some parts of the ocean there's a thick layer of sediment that gradually rains down from above, building up year after year after year. What they do is they push this in, and they have a piston that comes up, sucking in a core. And you end up with cores like this of different depths of the material in the floor of the ocean. It can be done in oceans, it can also be done in lakes. Now, some places this is useful, some places it's not. Some places the bottom of the ocean or the lake is being scoured by water. Sometimes there are landfills, but there are some places where for hundreds of thousands of years sediment has just been steadily, quietly accumulating, and you can see clear layers. And to some extent you can use radiocarbon dating to work out how long ago the deposits were laid down. That doesn't go too far back, but there are other dating techniques that go further back. Okay, so you can find a bit of rock that was laid down there, say 100,000 years ago. How could you work out what the temperature was? Well, you basically use life forms in them. You either use pollen grains, normally in lakes. For example, if you see lots of pollen of a particular plant that only grows at high temperatures, you know that the area around the lake where it was laid down was full of those plants. That gives you one sort of weather measurement. The most common and powerful technique, though, is to use microscopic organisms called foraminifera, or forams. So here we have some live forams. These are tiny things that float in the water, and then when they die, they leave calcium carbonate shells which sink gradually down to the bottom and pile up, and that's what you can find. The study of these things is called palynology. Actually, my very first job before I went to university was helping out with palynology for North Sea oil exploration. And people called palynologists will study these fossils and use it to date rocks, because as they evolved, you can look at a slice of rock from beneath the seafloor from 70 million years ago and say, oh yes, this particular foram only appeared 65 million years ago and died out 57 million years before, and so you can work out the dating. But also you can use them to work out the temperature. And how this works is a truly remarkable story of isotope ratios. Now, what's an isotope? An isotope is an atom which has this normal number of protons and electrons, but either too many or too few neutrons. The two isotopes that really matter here, one is hydrogen. Now, water is normally made of one hydrogen, which just contains one proton, and water, 16 oxygen, which means oxygen has 8 protons and 8 neutrons to give it a total atomic mass of 16. But occasionally you find a hydrogen atom which, instead of having just a proton in its nucleus, has a proton and a neutron. This means it's called deuterium, and it will be called 2H. You also get occasional oxygen atoms in which you've got 2 more neutrons, so 8 protons and 10 neutrons. So that would be oxygen 18. There's also a bit of oxygen 17, but we won't worry about that for the moment. So these are isotopes, and they're perfectly stable. Deuterium lasts forever, oxygen 18 lasts forever. They are stable nuclear isotopes. The fact that you've got a small amount there actually just reflects how they were formed in stars in the billions of years in the past. And these isotopes are very rare. So, for example, it's about 0.2% of oxygen atoms are the oxygen 18. The other 99.8% are the normal oxygen 16. But it is possible to take water or any other form of oxygen, put it through a mass spectrometer, and actually measure the fraction of these isotopes. And what people discovered, starting in the 60s, is that in water, the ratio of these isotopes, it applies to both deuterium, but I'm going to mostly show you the oxygen isotope ratios, but the same thing applies to deuterium, depends on the temperature. Here, for example, is the precipitation in Bern, Switzerland. So people have collected either the rain or the snow that's falling on that particular day, and they've compared it to the month and the temperature in the month. And what you can see is the rain that fell in summer, when the temperature's up around 20 degrees, has a different ratio of, this is how much parts per 1,000 there are of the isotope oxygen 18. And it's depleted a little bit there, and it's depleted much more when it's cold. So the ratio of oxygen 18 to oxygen 16 depends on the temperature. And this has been seen in many cases. For example, you can look at the tree rings, and you can take the cellulose in a tree ring and measure the oxygen in that cellulose, and that will tell you what the ratio of O16 to O18 was when that particular part of the tree ring grew. And you can compare that against weather records for the last 100 years, and again you see this correlation. You can also look at foraminifera shells included in the calcium carbonate. The carbonate has oxygen in it, and you can look at the ratio of oxygen 18 to oxygen 16 in the calcium carbonate. This is a really difficult measurement to make because you're grinding up tiny amounts of shell and then measuring the oxygen, and you don't want to let any oxygen in while you're doing it. If you breathe on it while it's happening, it's going to get contaminated. If there is oxygen adsorbed into the walls of the metal in your pipes, that can give you problems. But the researchers have had lots of trouble with this, but over the years they've worked out how to do it. Many of these researchers in the School of Earth Sciences here at the ANU. And you get a nice clear correlation over a large range of temperature between the percentage of oxygen 18 to oxygen 16 against the temperature. Okay, so what's going on here? Why? The trouble is with isotopes is they're chemically identical. Like oxygen 16 and oxygen 18, they've got the same electrons and the same energy levels, so chemically it does all the same bonds. It doesn't behave differently chemically to normal oxygen. So how can temperature cause things to split off? Well, we think what's going on is this. In some sense it doesn't matter because these correlations speak for themselves, but you'd like to understand why the correlation is going on before you trust it. So the first effect is you get water evaporating, typically from the sea, and the light isotopes evaporate a bit more easily, partially because they're lighter and also because the bond energy holding them together is a bit less, and that means they can more easily escape into the air. So you find that the clouds, which mostly form in hot regions, have slightly more light isotopes, and the heavy isotopes are left behind in the water. Then the atmosphere can carry those clouds towards colder regions, and as the clouds are carried, rain falls. Some of this water vapour condenses, and once again there's a slight tendency now for the heavier isotopes to fall out more easily, because they're heavier. The chemistry is not really different, but because they're a bit heavier they can bond and they have more gravity, and so the rain tends to be enriched in oxygen 18 and deuterium, leaving behind more, once again, of the light isotopes. And then when they get to some polar region and they fall and they produce snow, this is going to be enriched in light isotopes. And this whole process depends a bit on the temperature. It turns out when it's colder, the weather bands contract towards the equator, and so the heavy isotopes fall out close to the equator, so you get more light isotopes making it further from the equator. So you actually get different correlations depending where you are, but this has all been studied at great length, and I think it's now fairly well understood.